Hey everyone, and welcome to a deep dive that might just turn your world upside down.
Literally.
Yeah, well, maybe not literally, but it's going to make you question something
Yeah.
that you probably experience every single day without even thinking about it.
Mm-hmm.
Gravity.
Exactly. We're going to explore this theory
Okay.
that suggests maybe everything we think we know about gravity might not be the whole story.
I am intrigued already.
So are we.
So where are we getting this mind-blowing information from?
All right, so the source for today's deep dive is a YouTube video from the channel Atlantean Astrology.
Okay.
And the video is called The Divine Blueprint, Unveiling the Architect of the Universe.
Okay, the divine blueprint. I like that.
Yeah.
So we're talking about a theory of gravity
Yes.
that comes from a channel called Atlantean Astrology.
That's right.
So I am sensing that this is not going to be your typical physics lecture.
You are sensing correctly.
Okay, good, good. I like where this is going.
What's really fascinating about this is we're not just talking about like a minor tweak to our existing understanding of gravity. This theory actually flips the script.
Okay, flip the script. How?
It suggests that instead of a pull, gravity might actually be a push.
Wait a minute, hold on.
Yeah.
Gravity is a push.
That's what this theory proposes.
I mean, I thought we had this all figured out. You know, Newton,
Right.
the apple, the whole thing.
Yeah.
It's what keeps our feet on the ground. It keeps the planets orbiting the sun. So how on earth could it be a push?
I know, right? It seems completely counterintuitive.
Yeah.
But that's what makes this theory so fascinating.
Oh, hey.
It dares to challenge a fundamental concept that we basically take for granted.
All right, so before we dive into this whole push idea,
Sure.
let's take a step back.
Yeah.
What are some of the things that puzzle scientists about gravity as we currently understand it?
So one of the biggest mysteries is something called dark matter.
Okay.
Dark matter, the invisible stuff. The invisible stuff. Exactly.
Right.
Astronomers observe how galaxies rotate, and they're spinning way faster than they should
Okay.
based on the visible matter that we can see.
So it's like there's this extra gravity
Right.
that we can't account for.
Right, like there's some kind of invisible scaffolding holding these galaxies together, keeping them from just flying apart.
Right. So they call this invisible stuff dark matter.
Exactly, because it doesn't interact with light. So we can't see it directly.
Okay. But we know it's there.
We know it's there because of the effect it has on the stuff that we can see.
Okay, so it's like a cosmic ghost
Yeah.
exerting its influence, but we can't actually see it.
Pretty much.
Okay, so that's dark matter. What else?
So then there's dark energy.
Okay, dark energy. This one's even weirder, right?
Yeah, even weirder.
Right.
So dark energy is thought to be
Okay.
the force that's driving the accelerated expansion of the universe.
Okay, so it's pushing everything farther and farther apart. Okay, so dark matter is holding things together.
Like the glue.
And dark energy is pushing things apart.
Right, like the anti-glue.
So our universe is like this cosmic tug of war.
Kind of, yeah. It's a very dynamic place.
Right, but here's the thing. Don't these concepts...
Dark matter and dark energy.
Yeah, kind of clash with our current models of gravity, like Einstein's theory of general relativity?
They don't fit neatly.
Right.
Einstein's theory does a great job of explaining a lot of things about gravity, especially on like planetary scales and stars.
Okay.
But when you start talking about dark matter and dark energy,
Yeah.
it starts to break down a little bit.
So is that where this grand Fibonacci theory comes in?
That's exactly where it comes in.
Okay, so this is where we flip the script.
We flip the script.
And say gravity's a push.
That's right. It's proposing this radical idea that gravity isn't a pull from mass, but a push generated by the interplay of what it calls a subtle magnetic field, or SMF.
Okay,
SMF and the relative vacuum of space, which are called RVs.
RVs. All right, so we got SMFs and RVs interacting to create a push.
Right.
So how does this push create something that feels like the pull of gravity?
Okay, so try to picture this. Imagine a balloon being inflated.
Okay.
The surface of the balloon represents space, and the air pushing outward represents the SMF and the RVs.
Okay.
As the balloon expands anything on its surface.
Like little dots representing galaxies?
Yeah, exactly. Would naturally move apart.
Okay, so the galaxies aren't being pulled apart. They're being pushed apart.
Pushed apart by this outward force.
Pushed apart by this outward force.
And this outward force, this is what they're calling gravity.
That's what this theory proposes.
Okay, so if everything is being pushed outward, Why do we feel a pull towards the Earth?
So the theory says that this SMF, this subtle magnetic field, is incredibly subtle.
Mm-hmm.
Its effects are most noticeable on like vast cosmic scales.
Okay.
Here on Earth, the pull of the planet's mass overwhelms that subtle universal push.
So it's not that the pull of gravity is an illusion.
It's just that there's this bigger, more fundamental force at play
Exactly.
that we don't really perceive on our everyday level.
It's all about perspective.
Okay.
You got to zoom out,
Right.
look at the bigger picture
Okay.
to really see how this push could be driving the structure of the universe.
Okay, I think I'm starting to wrap my head around this a little bit.
Go ahead.
What about black holes?
Ah, yes, black holes.
I mean, aren't those like the ultimate example of gravity's pull?
Right. The classic understanding is that they suck everything in.
Yeah.
But this theory has a different take on black holes.
Okay, let's hear it.
So instead of being points of infinite collapse,
Mm-hmm.
it views black holes as finite zones of saturated vacuum.
Saturated vacuum, what does that even mean?
So imagine it like a cosmic drain
Okay.
where the RVs, these relative vacuums, have reached like a maximum density. Matter and energy get pushed into this zone by the SMF,
Mm-hmm.
not pulled in by the black hole's gravity.
Okay, so instead of being crushed into a singularity,
Mm-hmm.
there's like a limit to how much the vacuum can be squeezed.
Yeah, like you can only squeeze a sponge so much before it pushes back.
Okay, so that's how they explain black holes.
That's one way this theory explains it.
All right, well, this is definitely a lot to take in,
It is.
but I am already fascinated.
Me too, and there's even more to explore.
Okay, well, I am all ears. Bring on the cosmic weirdness.
Oh, we've got plenty more where that came from.
Good, because we've only just scratched the surface of this theory.
We've got neutron stars. We've got fractals.
Fractals.
Okay, now we're talking.
We're going deep down the rabbit hole.
I am ready. Let's do it.
All right, let's dive in.
All right.
So the theory suggests that even the smallest and densest objects in the universe, and neutron stars,
yeah.
are influenced by this universal push.
Okay.
It proposes that these incredibly dense objects are stabilized
Hmm.
by this constant push of the RVs.
Okay.
And their rapid spins could be tapping into like a hidden reservoir of magnetism
Oh, wow.
linked to the SMF.
So even though we can't feel it, right,
This cosmic push is influencing everything.
from the largest galaxies to the tiniest subatomic particles.
Wow, so it's all connected.
That's where the concept of fractals comes in.
Okay, so fractals.
Yeah. The theory suggests that this push mechanism operates on all scales,
Mm.
creating a kind of fractal pattern where the same basic principle repeats itself
Okay,
at different levels of magnification.
like those beautiful snowflakes.
Exactly.
They all have that same basic pattern, but they're all unique.
Right. And this fractal nature of the universe
Yeah.
could be the key to understanding how everything is interconnected.
So it's like this cosmic dance
I like that.
with everything moving and interacting in this intricate, interconnected way.
Precisely.
That's incredible. I mean, it's kind of beautiful when you think about it.
It is. It's a very elegant theory.
Okay, but we can't ignore the elephant in the room.
The divine blueprint.
Yes.
Right.
Where does spirituality fit into all of this?
That's where the theory gets even more thought-provoking. The video suggests that this push mechanism, this underlying harmony,
Mm-hmm.
this interconnectedness in the universe, could point to an intelligent design.
Okay, so we're talking about the possibility of a divine architect.
Right. The video uses that term.
So this isn't just a scientific theory.
Right.
It's also opening up a conversation about the potential intersection of science and spirituality.
Exactly. It's not saying that this theory proves the existence of God
Right.
or any specific religious belief.
Okay.
But it does raise some interesting questions about the nature of the universe
Yeah.
and whether there might be something more to it than just random chance.
Okay, well, I am definitely feeling like my mind has been blown wide open.
Just a little bit.
Yeah, just a tad. We've gone from dark matter
Mm-hmm.
and dark energy to black holes and fractals.
Yeah.
All through the lens of this radical new theory of gravity.
It's quite the journey.
It is, and we're not done yet.
Oh, no. We've got more to explore.
All right, so we've laid the groundwork.
We have.
We've established that this theory proposes a pretty major shift
Yes.
in our understanding of gravity.
Yes.
But how does this push idea actually explain some of the specific cosmic puzzles that our current models struggle with?
That's a great question, and that's what we're going to dig into next.
Okay. I am ready for more buckle up, everybody, because this deep dive is about to get even deeper.
Definitely buckle up.
So we've laid the groundwork. We've established that this theory proposes a pretty major shift in our understanding of gravity. But how does this push idea actually explain some of the specific cosmic puzzles that our current models struggle with? You mentioned dark matter earlier. Let's dig into that a bit more.
Yeah, absolutely.
Okay.
So as we touched upon, the way galaxies rotate is one of the biggest pieces of evidence for the existence of dark matter. They spin much faster than they should based on the amount of visible matter we can observe.
Right. It's like there's some invisible hand holding these galaxies together, providing the extra gravitational pull to keep them from spinning themselves apart.
Precisely. And the prevailing theory is that this invisible hand is dark matter, a mysterious substance that makes up the vast majority of matter in the universe, but which we can't see or interact with directly.
So how does the Grand Fernacci theory approach this conundrum? Does it offer an alternative explanation for this missing gravity?
It does. Instead of invoking dark matter, it suggests that the interaction between the SMF and the RVs creates a kind of outward pressure that influences the way galaxies rotate. It's like an invisible scaffolding, not holding the galaxy together from the inside, but pushing it inward from the outside.
Okay, so instead of dark matter halos surrounding galaxies, we have this invisible push from the SMF and RVs. But wouldn't this push act on everything in the universe, not just galaxies?
Exactly. And that's one of the fascinating things about this theory. It suggests that this push is a universal force influencing the movement of all celestial objects. It's just that on the scale of galaxies where the visible matter is spread out over such vast distances, this subtle push becomes the dominant gravitational force.
So our entire understanding of galactic dynamics might need a complete overhaul if this theory turns out to be correct.
It would be a revolutionary paradigm shift, for sure. And it's not just galaxy rotation. The Grand Fernacci theory also proposes a completely different way of thinking about black holes.
Well, black holes are already one of the most mind-bending concepts in astrophysics. How does this new theory add to the mystery?
Well, as we discussed, traditional theories describe black holes as regions of infinite density where matter collapses to a singularity, a point of zero volume and infinite gravity.
And that singularity idea creates some pretty big theoretical headaches, right? Like what happens to information that falls into a black hole?
You get it. The laws of physics suggest that information can't just disappear. But if you get sucked into a singularity, it's gone forever. That's been a major point of debate among physicists for decades.
So how does the Grand Fernacci theory address this problem? Does it get rid of the singularity altogether?
It does. Instead of a singularity, it proposes that black holes are finite zones of saturated vacuum. It suggests that there's a limit to how much the vacuum of space can be compressed. It's like trying to squeeze a sponge. You can only compress it so much before it pushes back.
So instead of everything being crushed into an infinitely small point, matter and energy get pushed into the zone of maximum vacuum density, but they don't actually collapse to a singularity.
Exactly. And this alternative view of black holes changes how we think about their role in the universe. Instead of being these monstrous, all-consuming entities, they become part of a dynamic process of push and interaction, perhaps even playing a role in redistributing matter and energy throughout the cosmos.
That's a much more appealing image, but I'm still trying to wrap my head around this idea of a push governing the universe. It feels so counterintuitive to how we experience gravity here on Earth.
I understand it's a big leap from the familiar pull of gravity that keeps our feet on the ground. But remember, the Grand Fernacci theory proposes that this push operates on all scales, from the smallest particles to the largest structures in the universe.
So even though we don't feel it directly, this cosmic push is influencing everything around us? Are you saying that even the chair I'm sitting on is being subtly affected by this universal force?
Precisely. And that's where the concept of fractals, which we touched on earlier, comes in the theory. Suggests that the universe is built on a kind of fractal pattern, where the same push mechanism repeats itself at different levels of magnification. It's like zooming in on a coastline. You see the same basic patterns of inlets and bays no matter how closely you look.
So it's not just a cosmic push, it's a cosmic push within a cosmic push, within a cosmic push. It's mind-boggling to think about.
It is, and this fractal nature, according to the theory, could be the key to understanding how everything in the universe is interconnected.
Okay, I think I'm starting to see the bigger picture here, but I have to ask, if this push is everywhere and always acting, why don't we feel it? Why do we still experience gravity as a pull?
That's a great question. And it gets to the heart of how the Grand Fernacci theory reconciles its core idea with our everyday experience. Remember, the SMF is described as being incredibly subtle, Its effects are most noticeable on cosmic scales, where vast distances and huge amounts of matter and energy are involved.
So on the scale of our planet, the pull of Earth's mass overwhelms this subtle cosmic push. That's why we don't feel like we're constantly being pushed upward.
Exactly. It's like trying to hear a whisper in a hurricane. The whisper is there, but it's completely drowned out by the much louder noise.
So the Grant Fibonacci theory isn't saying that the pull of gravity we experience is an illusion. It's just that there's a much bigger, more fundamental force at play that we don't usually perceive.
Precisely. It's like looking at a tapestry up close. You see the individual threads and colors, but you don't necessarily grasp the overall pattern or design. You have to step back to appreciate the whole picture.
So this theory is trying to give us that bigger picture, that cosmic perspective on how gravity might actually work.
Exactly. And it's not just reinterpreting the gravity we already know. It also offers an intriguing explanation for one of the biggest mysteries in cosmology, the accelerating expansion of the universe.
Right. We talked about dark energy earlier, which is the mysterious force that scientists believe is driving this expansion. Does the Grant Fibonacci theory offer an alternative explanation?
It does, and it does so without needing to invoke dark energy at all. Remember how we talked about the SMF and the RVs interacting to create this cosmic push? Well, according to the theory, this push isn't constant. It's actually increasing over time as the universe expands. The relative vacuum of space becomes even more empty, if you will, creating a stronger push outward.
So instead of a mysterious dark energy pushing everything apart, it's simply the vacuum of space becoming more, well, vacuumly, and thus exerting a stronger outward force.
Exactly. It's like as the balloon of the universe expands, the air inside it becomes less dense, but the pressure pushing outwards from that less dense air actually increases. That's what's driving the acceleration of the expansion.
That's pretty elegant, I have to admit. It gets rid of this mysterious, unknown entity, dark energy, and explains the expansion in terms of this underlying push that's already at the heart of the theory.
Right, and that's one of the most appealing aspects of the Grant Fibonacci theory. It attempts to explain some of the biggest cosmic mysteries using a single unified framework. It's like finding the missing piece of a puzzle that suddenly makes everything click into place.
Okay, so it's an elegant theory, it explains some major cosmic puzzles, and it challenges our assumptions about something as fundamental as gravity, but I'm sure it's not without its critics.
You're absolutely right. Well, the Grant Fibonacci theory is certainly intriguing. It's still a radical departure from mainstream science, and it faces some significant challenges. We'll delve into those next.
All right, so we've been on this incredible journey exploring this idea that gravity might actually be a push rather than a pull. And this Grant Fibonacci SMF-RV theory, it really offers some interesting explanations for some big cosmic mysteries, things like dark matter, black holes, and even the accelerating expansion of the universe. But you mentioned that there are some challenges to this theory. What are some of the hurdles it needs to overcome to be taken seriously by, like, the mainstream scientific community?
Yeah, so one of the biggest challenges is that the theory relies on the existence of a subtle magnetic field, an SMF, that permeates the entire universe. And according to the theory, it's this SMF that interacts with the relative vacuum of space to create that cosmic push.
And the problem is we've never actually detected this SMF, right? It's still a hypothetical concept.
Exactly. And while the idea of such a field is plausible, and there might be indirect evidence to support its existence, scientists haven't been able to directly measure or observe it yet.
So it's kind of like dark matter in a way. We can see the effects, but we haven't actually seen the thing itself.
That's a good analogy. And to gain wider acceptance, this theory needs to provide a way to test for the presence of this SMF. Like, what kind of experiment could be designed to detect it? What are its properties? How does it interact with other known forces? These are all questions that need to be addressed.
So it's not enough to just propose this new field. The theory also needs to provide a roadmap for how we can actually verify that it exists.
Yeah, extraordinary claims require extraordinary evidence.
I've heard that somewhere.
And then there's the question of how this push-based gravity fits in with our current understanding of physics, specifically general relativity and quantum mechanics.
Okay, those are the two big pillars of modern physics, and I know that they haven't exactly been easy to reconcile with each other.
Not at all. General relativity does a great job of describing gravity on large scales, things like planets, stars, and galaxies. But quantum mechanics that governs the world of atoms and subatomic particles.
And this theory is proposing a completely different mechanism for gravity. So how does it bridge the gap between these two seemingly incompatible worlds?
That's a major challenge. The theory needs to demonstrate how its push-based gravity model can account for all the phenomena that general relativity and quantum mechanics already explain so well. It can't just explain away dark matter and dark energy. It needs to also explain everything else that we already know about gravity.
So it's not just about overturning our current understanding, it's also about building a new framework that encompasses all the existing knowledge while also explaining the things we've been struggling with.
Exactly. It's a tall order for any theory.
It is. So what's the takeaway for our listeners who've been with us on this deep dive? Should we all be packing away our physics textbooks and rewriting the laws of gravity?
I wouldn't say we're there yet. It's important to approach new ideas with both excitement and a healthy dose of skepticism, this Grand Fibonacci theory. It's a fascinating thought experiment, and it highlights some of the limitations in our current understanding of gravity. It might spark new avenues of research, lead to new discoveries, and who knows, it might even revolutionize our understanding of the universe. But for now, it's still very much a work in progress.
So it's not time to throw out Newton or Einstein just yet, but it's worth paying attention to these new ideas and seeing where they lead. After all, that's how science advances. By constantly questioning, exploring, and pushing the boundaries of what we think we know.
Precisely. And beyond the scientific implications, this theory also invites us to think about the universe in a new way, to contemplate the possibility of interconnectedness on a cosmic scale, and to consider the potential for a deeper meaning behind the workings of the cosmos.
That's what I love about these kinds of discussions. They challenge us to think beyond the equations and the data and to grapple with those bigger questions about our place in the universe. And even if this specific theory doesn't ultimately hold up, it definitely sparks a sense of wonder and reminds us that there's still so much out there that we don't know.
Absolutely. And that sense of wonder, that drive to explore and understand, is what fuels scientific progress and expands our horizons.
Well said. This deep dive has been quite the journey, from the familiar pull of gravity to the mind-bending possibility of a cosmic push, from dark matter and black holes to fractals and the accelerating expansion of the universe. And along the way, we've encountered some really profound questions about the nature of the universe and our place within it.
It certainly has. And whether you come away from this deep dive convinced by the Grand Fibonacci SMFRV's theory or not, I hope it's ignited your curiosity and inspired you to keep exploring the mysteries of the cosmos.
To our listeners, thank you so much for joining us on this incredible adventure. Keep asking those big questions, keep looking up at the stars, and most importantly, never lose that sense of wonder. Until next time, keep exploring.